Good morning everybody and welcome to Cracked Pot Chemistry. On today's revision video we are doing topic 10 using resources from the CGP AQA chemistry textbook, which is this one right here. In topic 10 we are covering alloys, corrosion, finite versus infinite resources, sustainability, recycling, life cycle assessments, potable water and water treatments, the harbour process and fertilizers. Topic 10. Using resources. Ceramics are non-metal solids that are not made from carbon but still have high melting points. Some are made from clay, which is soft when dug up so can be moulded. When it is fired at high temperatures, it hardens to form a clay ceramic. These features make it really useful for pottery and bricks. Glass is another type of ceramic that can be moulded when hot and brittle when cold and thin. It is also generally transparent. Most glass is made from a mixture of limestone, sand and sodium carbonate, which is heated until melting, then cooled to become a glass. Borosilicate composites are generally made of two materials. Fibers act as reinforcement are surrounded by a matrix acting as a binder, e.g. fiberglass is glass fibers in a plastic matrix. It's low density and high strength, meaning it is used in things like skis, surfboards and boats. Other good examples are carbon fiber and concrete and wood. Polymers can be low or high density. Low density polyethylene is made at moderate temperature, high pressure and with a catalyst. It is very flexible, so is used in bags and bottles. High density polyethylene is made at low temperature and pressure with different catalysts, so it is used for water tanks and drain pipes. Polymers can also be thermosetting or thermosoftening. In thermosetting polymers, the monomers form crosslinks between the chains, holding them together in a solid structure, so they are strong, hard, rigid. Thermosoftening polymers contain polymer chains that tangle together with weaker forces between the chains. This means that they can be melted and remoulded. It is good to remember these properties, as in an exam you could be asked how suitable they would be to suit a particular purpose. Alloys are made because metals on their own are usually too soft, and mixing them together creates a very strong material, e.g. low carbon steel, the 0.1 to 0.3% carbon, is easily shaped and is used in car bodies, whereas high carbon steel, 0.22 to 0.25% carbon, is very hard and inflexible, so it is used in cutting tools and bridges, whereas stainless steel is different again, as it contains chromium and sometimes nickel, which are both corrosion resistant and are used in cutlery and containers for corrosive substances. Other examples include bronze for making statues, brass for taps and door fitting, gold alloys in jewellery and aluminium in aircraft. Corrosion is the gradual destruction of metals due to their reacting with other substances. Iron and iron alloys rust very easily by reacting with water and oxygen, which are both present in the air. This forms a hydrated iron 3 oxide compound, and only happens on the surface of the material where it is exposed to air. Rust is very crumbly, and soon fall off, leaving more iron available to rust again. This process happens gradually, but can lead to entire objects, such as cars and bridges, corroding away. Aluminium also corrodes, but unlike iron, things that aluminium oxide forms acts as a protective layer and stops any further reaction from taking place. To prove air and water are needed to rust, you can do an experiment with 3 test tubes. One with just water, boiled so it has no air in it, one with just air, with calcium chloride to soak up water, and one with both air and water, as shown. The mass of the rusty nail will also increase. There are 2 main ways to stop this from happening, either by coating the iron with a barrier, e.g. paint or plastic, electroplating with a different metal, and oiling or greasing. The other way is a sacrificial method by putting a more reactive metal in with the iron, such as zinc or magnesium, which will react with the water or air first instead of the iron. The most efficient way to do this could be to spray a coating of zinc, for instance. Natural resources form without human input. Some resources that we used to rely on, such as rubber, can now be replaced with man-made materials such as polymers. Agriculture is a process where we provide the right conditions to exploit a natural system, such as growing plants for food. Renewable resources can form at the same rate or more as we use them, e.g. trees, crops, and in some places fresh water. Non-renewable or infinite resources are not formed quickly enough, or at all, to be used forever by human consumption. These include fossil fuels, nuclear fuels, and most mining metals. Extracting finite resources is very bad for the environment, both on a local and global scale. Sustainable development aims to develop in a way that considers the needs of present society, whilst not damaging the lives of future generations. Extracting and refining or processing these resources can be unsustainable because of how they're powered, so reducing our dependency on finite resources is very important. For example, copper ores which are low grade can still extract copper using natural ways, e.g. bioleaching, where bacteria separate out copper compounds from the ore in solution, which can then be extracted via electrolysis, or by phytomining, where plants grown in copper soil can be harvested and burnt and electrolyzed to produce copper. These new methods are much more sustainable, but slower than traditional methods. Recycling can reduce or replace the need for mining or extracting materials, and reduce the amount that goes to landfill. Metals can be easily recycled by melting and reshaping them. Glass bottles can easily be reused without reshaping them, and can be sorted, crushed, or melted into new bottles, or insulation for people's homes in glass wool. Life cycle assessments look at a product across a lifetime and determine the impact it would have on the environment. Number 1. Getting raw materials, e.g. through mining, is very environmentally damaging, and processing these takes a lot of energy, e.g. fractional distillation of crude oil. Number 2. Manufacturing also uses energy and creates pollution, which could be reduced if other uses are found for the pollutants. Number 3. Using the product can hurt the environment, e.g. how fuels are burnt, or how long a product can be used before it is scrapped. Number 4. Product disposal in landfill or polluting rivers, and the energy it takes to move it to its disposal site, as well as incineration, which releases more pollutants into the atmosphere. Comparing life cycle assessments for, e.g. paper and plastic bags, actually shows plastic bags might be the better choice, because they can be used for far longer than paper ones can. There are some problems with the life cycle assessment, e.g. it is difficult to give a value for the effect the pollutants have on the environment, or the visual pollution of plastic bags being left around. Furthermore, it is objective and thus can be biased to the values of the person assessing it, and selective LCAs can be biased in favour of a company's advertising by only showing the positive impact of a product. Potable water is water that is safe for human consumption. It is not pure, as it contains some dissolved salts, but has a pH of 6.5 to 8.5, and no nasty bacteria in it. Rainwater is a type of fresh water, and once it drains and becomes groundwater, we process it by filtration through wire mesh. Sand, gravel, and sterilisation through bubbling chlorine, gas, ozone, or ultraviolet light through it. In some countries there isn't enough groundwater, so seawater is distilled to make clean water instead. It could also be done through osmosis of membranes, but both these options are expensive and require lots of energy, so don't really produce a lot of water. Water can be tested and distilled in the lab. First, find the pH, should be between 6.5 to 8.5, and then test for the presence of sodium chloride by using a flame and nitric acid tests. Then, distill the water by boiling in a flask and allowing the stream to condense back down to another beaker. Then repeat the tests above to check that the salt and other impurities have been removed. Wastewater comes from many sources, such as agriculture, home usage. Sewage must be treated, wastewater from industrial processes, and removing of harmful chemicals to safely release into the environment. Treating wastewater at sewage plants, however, takes several steps. First, any large debris and grit are filtered off. Then, in a process called sedimentation, the sewage sits in a tank, and the heavy stuff falls to the bottom, and the lighter effluent floats on top. This is then removed and treated with air to encourage aerobic microbe breakdown activity. The sludge at the bottom is also transferred off, and gets broken down by anaerobic bacteria into methane gas for fuel use, and everything else can be used as a fertilizer. Now, this may sound disgusting, but recycling the nutrients that comes out of our bodies It's really important in ensuring that the soil can continue to grow food. Everything else is purified into clean water and let off into the streams and rivers. Mostly. See the video linked. In terms of energy usage, sewage requires more treatments than fresh water, but still less than desalination, so can be used as an alternative source in countries where water is scarce. The harbour process is a really important process to learn about, not only because its discovery led to us being able to sustain a larger world population, but also because the equilibrium, rates and yield of the reaction are all topics that are studied in a lot more depth at AS and A level. The Harbour process reaction is very simple. Nitrogen and hydrogen bind together to make ammonia in a reversible reaction. The nitrogen is usually sourced from the air, and hydrogen usually comes from steaming methane. However, this may change in future with more renewable sources of hydrogen becoming available. Both of the reactant gases are pumped at 450 degrees C and 200 atmospheres over an iron catalyst and a 3:1 hydrogen to nitrogen ratio. Because the reaction is reversible, not all the products will turn into reactants, but those that do will turn into a liquid in the condenser and be pumped off. The remaining gas is recycled, so nothing is wasted. The ammonia is then processed further to make ammonium nitrate, which is a great fertilizer. But to make the reaction at the best rate, especially at a low cost, compromise conditions can be made, such as those in the graph here. The reaction is exothermic, so the temperature must be low enough to have a good yield, but also high enough to keep the rate up. 450 is a nice middle ground. 20 seconds for a 10% yield sounds low, but is much more cost-saving than waiting 60 seconds for a 20% yield. Pressure, on the other hand, works better at higher atmospheres in terms of rate and yield, but at very high pressures are too expensive and dangerous, so a compromise is used of 200 atm. Also remember that the catalyst doesn't affect the equilibrium, just the rate of reaction. It helps it to go faster. Fertilizers are very important to feeding the world's growing population. They are slightly better than manure because of their availability, ease of use, lack of smell, and efficiency in rejuvenating the soil. The three main elements that each plant needs are nitrogen, phosphorus, and potassium, without which the plant cannot grow and are likely to have been depleted from the soil by previous crops. Fertilizers increase crop yield by making sure plants always have enough of these to continue growing and creating food. Npk fertilizers, nitrogen, phosphorus, and potassium, are formulations of salts that help plants do exactly that. Ammonia plus oxygen or water can make nitric acid. Nitric acid plus more ammonia makes ammonium nitrate, which is a great fertilizer. In industry, it is made in giant vats at high concentration, so it creates a lot of heat, which evaporates the water from the mixture to make a very concentrated product. In the lab, however, this is done through titration and crystallization at lower and safer concentrations to give crystals. This is obviously much slower but safer for school students to use. The potassium chloride or sulfate can easily be mined and used. However, when phosphate rocks are mined, the salts inside are insoluble, so they are reacted with an acid to make it soluble. Reaction with nitric acid makes phosphoric acid and calcium nitrate, or reaction with sulfuric acid makes calcium sulfate and calcium phosphate. Hey guys, thank you so much for watching. Don't forget to like, subscribe and download this PowerPoint, which was used in the video down in the description. I may also put in some bonus questions. See you later.